programming, it's a good idea to know about computers. I mean, if you really write big programs, you need to know limitations of computers. Okay, I will describe that, like how much memory is there, what is the computing power. So it's relevant. I mean, I don't know, you may know already about it, but let's review it. In fact, I will ask questions on this in the homework. So let's look at some of the stuff, and it's really changing very fast. I can't cope up with what is happening in the processors. The speed is increasing every year. So if you are in the supercomputing sector, then you need to be up to date. Okay, so we'll see. I mean, this, my data is slightly old, but it's rapidly changing. Okay, so let's first focus on desktop computers. That too is changing very fast, but it will give you an idea. In fact, the design remains the same. The units are getting more and more powerful. Okay, so the components of a desktop computers are like the computation unit, called CPU, memory, and input output. Okay, so this is von Neumann structure. Von Neumann kind of thought about this idea. In our brain, these two are, in fact, he segregated these functions, these three units. In fact, you will see that there are different units in a computer, but our brain does it in for all three in somewhat same place here, right? Of course, we get data from various places of the body, but memory and CPU is done by neurons. Okay, so it's not clear how we do it in computation in the brain, but anyway, this is the design of a computer by basically von Neumann. Some people say Turing had similar ideas, but the design of Turing was classified, so we don't know much about Turing's. Well, we know much about something about it, but von Neumann gets the credit, but Turing had done similar work. Okay, so if you look at inside the computer, which I think you should, so you see something like motherboard. Okay, this is a motherboard. Okay, so CPU sits here. In fact, there is a fan which cools the CPU, so there will be a fan which will be sitting on top of it. There are clever design to take the heat out. It's very hot. In fact, typically it's around 60 degrees, 50, 60 plus degrees temperature. So you have to cool it, otherwise it will just burn. So this is a processor, CPU. So I said processing unit. Most of the all computers, computation is done here. Then this is called RAM, random access memory. Okay, RAM. So these are RAM slots, but the RAM looks like this, and we put quite a few of these units. Okay, these units actually this is weak, I think. So quite a few of these units are placed here, right here. Okay, so that is placed there. So this is where your data sits, live data. There is something called hard disk. That's also memory. This one hard disk, and that hard disk is connected from the CPU, from this motherboard to somewhere else. Okay, so this is memory. These two are memory. So CPU is here, memory is here, and interface is there are a lot of connectors. I don't want to get into that part, but there are a lot of connectors which will connect to input output, graphics cards, and so on. Okay, so you don't need to know all of it for this course, but it's interesting how it's evolving. So let's look at a little bit more. So it turns out nowadays motherboards come with not only single CPU, but you can place many CPUs. So there was one place, CPU sitting here, you can have 2 slots. So multiple slots, in fact you can put something like 8 CPUs in modern motherboards, 8 of them. So there are right now 2 CPUs sitting here, and there are connectors to RAM. Actually, unfortunately, it's not working. So this is a RAM connection. That is also RAM. So this CPU is connected to this RAM, but they'll talk with each other with this interface. Okay. Now we also have connection with PCI is connecting to other hardware like hard disk. Okay. So this is the present design. You populate more and more CPU. That's what we are going towards. Put more power in a motherboard. Now if you look at single CPU, so remember there are 2 CPUs. Now if you look at inside a single CPU, there are cores. These are called core, core is full processing unit within. So multiplication, addition, data transfer, all these are done by this single core has power of this. So you can think of Ravan, you know, so it has 10 heads. Right now this has 4 heads. Okay, so each head can do its function. So now there are CPUs which has 15 cores. They are designed for 60 cores by Intel. Intel already has 60 core CPU. If you look at the GPU cards, you heard of GPU, no? NVIDIA GPU, that has 2500 or 2000 these cores, okay, 2000 heads. So it has extremely large number of cores. That's why it can do things fast. There is something called cache. If you are doing computing, serious computing, they need to know about. So this is also memory, but the memory sits very close to the CPU. So more the distance, longer time will take to access. Why? Because all of them roughly move the speed of light. So the longer distance, delta t is L by C, speed of light. Okay. So closer you are, faster it is. The present bottleneck is the memory access. CPUs have gone very fast, become very fast. I will tell you some numbers, but the problem is RAM which is slow. Okay. Hard disk is, well, there is a hierarchy. Hard disk is slowest, then RAM, and then cache. Now this is called L3. There is something called L1 and L2 cache too. Okay. So there are hierarchy of caches. So some are fast, some are not so fast, but they sit very close to the core. Okay. Now if I put more and more data in cache, then my computation will be faster. Okay. So basically if your grocery store is close to your home, then you can get things fast, but it's far away, then it takes longer time. Okay. So it's precisely similar design. Okay. You bring it closer and closer and put more storage in cache. Okay. So you can look at the size. So this die size, this whole size is 160 millimeter squared. So how much is CPU die size? So like if you take the square root, 13 centimeter by 13 centimeter. So this is the size. Okay. And how many transistors are sitting there? 1.48 billion. Sorry, 1.4 billion. Okay. So huge number of transistors are packed in that unit. Okay. It's amazing that we could reach this kind of complexity. Okay. Now this is in a single layer. Now the idea is to put more layers and then of course connect it. So that's another direction people are working on. So this is roughly, I mean, of course you can do full cores on CPU itself. Okay. But for us we need to know how many cores, cache. This is also some of it. I am trying to inspire you that okay, there is more to computing than Python programming. Okay. Python programming is only a single step. You just get, you are like a kid, you know, so you have to grow from that point. So we worry about these aspects for efficiency in the code. Now let us look at some estimate how fast it can compute. So there is a clock. Every computer has a clock. Okay. Clock is like heart. Okay. So it will synchronize various processes in the machine. So in fact every clock cycle will say, you do this work. So it's all synchronized by a clock. This is a very important aspect. But how many floating point operations? Floating point is real numbers, real add, real multiply. How many operations can it do? It turns out it can do, in the modern machines, can do 8 operations per cycle. Okay. This is a good number to remember, 8 operations. So at additions, or well, it's also complicated. It can possibly normally do 4 multiplication and 4 addition. It's arranged in a pipeline, so it basically moves like assembly line. But this again I will not discuss, but it just that it can do 8 operations per cycle. Now how many cycles does it have per second? Typically it's 2.5 gigahertz, some are 3.5, but nothing at 5. Okay. This is a limitation. This is coming from microphysics, quantum limitation in fact. If you increase the clock speed, things are just not working out. Okay. The power requirement becomes more, there are a lot of issues. So we reached a bottleneck in terms of clock speed. There is no breakthrough in increasing the clock speed beyond 5 gigahertz. So how many operations can it do per second? It can do 20 gigaflops. Flop means floating point operations. FL is floating, op is operation. Okay, so it can do 20 gigaflop per second each core. Okay, that's huge number. I mean, I can probably do one multiplication in 1 minute. Okay, so this can do this many operations per second. Now, how many cores a desktop computer has? Typically, you are getting quad core machine, no? Quad core desktops or laptops. So quad means 4. So it has 4 cores per processor. So if you have a laptop with a quad core processor, it can do 80 gigaflop. So 80 G for giga floating point operations per. Okay. Now, but it turns out this is not enough for computing which we need now for advanced computing. This is really small. Okay. We will work out some numbers for slightly bigger problems in future, but it's huge power. I mean, this is really a big power. It turns out you can buy workstations which can do more than desktop. So there's a next class is called workstation. Okay, workstation will have better processor. You can put 8 of them, 8 CPUs. In laptops you can't put more than 2. So they will heat up, and your motherboard is not. It will of course cost more. Okay, so everything, if you need more, you need to pay more. So workstation, more RAMs. It can go up to 15 cores. So I put 6, 8, 10. We can also go to 15. But this is not enough for big computations. So I want to do weather prediction. This won't be enough. Okay, or if I want to simulate a DNA, this is not enough. Okay. So let's look at memory. So I'll just give you some idea about memory. Again, very preliminary idea. So here is all based on binary, classical computers. So it has 0 and 1. So two states, 0 and 1. So every storage or computation will be in binary. Quantum computers, if you know a bit of it, it has many states. Okay, so that's a big plus for quantum computation. But classical computers are zeros and ones. So this is another number, byte. I didn't mention it, but 1 byte is 8 bits. So instead of 8, you just say 1 byte. Typical PC has 4 to 8 GB. Okay, depends. I mean, I don't know how many have 16 GB RAM in your laptop. That will cost more money. Okay, so you normally you keep it 4 or 8. Okay, 8 is already rich laptop. PC also mean laptops are now as powerful as a PC. So this one word, I mean, this memory is also evolving very rapidly. So this is called DDR, is double data rate, but the names are changing almost every year. Now we have this fast switch, solid state RAM, solid state hard disk. Okay, so that doesn't have spinning parts, so that's quite fast. In fact, RAM and solid state device, solid state hard disk are roughly similar speed. Okay, so it's but RAM is faster definitely. So please remember the difference. Hard disk is outside. I didn't show you. If your hard disk will be a disk of this size, which will be not on the motherboard, it will be somewhere else, and RAM will be sitting on the motherboard. So if you are closer to the CPU, it's faster. So these are different names. So as I said, this technology is changing. So SDRAM is another new name for faster RAM. So I will not discuss that, but just to tell you that things are changing very fast. So we need to know little bit about how much storage is required for each unit of data. So character, so if I write a text, so like your SMS you are doing it, so each character is stored in the computer and each requires 1 byte, 8 bits. So you can see how many characters can I store in a byte. You know this stuff, no? This is school stuff. So if you have one bit, then 0 and 1, only 2 choices. If you have 2 bits, then I have 4 choices, 0 0 to 1 1. So if you have 8 bytes, 8 bits, then I have 2 to the power 8 options, and 2 to the power 8 is 256. Okay, these numbers again is easy. So, the characters we have 256 of them. So, A, B, C, D, there are numbers for each of them, A, B, C, D, E, F, G, H, like that, for alphanumerics, dollar, and so on. Nowadays, at least in the browsers, we have 2 bytes for a character, because multilingual. So, Hindi also you store as a number, you are not storing as a font, that will be too expensive to port. You understand, you don't want to send a image of so you are sending a code for a image will be more, it will take more bigger data. So, because of all this different language, so now characters are stored as 2 bytes. So, 16, so 2 to the power 16 characters, and 2 to the power 16 is how much? Okay, I will tell you a number, 2 to the power 10 is 1000, okay, you can just work it out. So, 2 to the power 16 will be 2 to the power 6 into 2 to the power 10, 64,000. So, you can store 64,000 characters in modern, because of this is called Unicode. Okay. So, Unicode is 2 characters. Integer in Python, it will be any integer, any length. So, you can store 64 digits, whatever digits you like. Python will adjust its length or how much bytes are required to store it. But it is also important to know what Fortran or C does. C will be assigning 4 bytes for a character, for an integer. Okay. So, 4 bytes integer will store maximum and minimum. So, this is a max. So, this is going to be 2 to the power 31, okay, because 1 will be sign bit. So, 1 is reserved for sign and remaining is 2 to the power 31. So, you get minus 2 to the power 31 to 2 to the power 31, and there is little bit of 2 to the power 31 minus 1. Okay. So, that is a bit technical issue, but you can store up to 2 billion. The number is can't be exceeding 2 billion for integer. Okay. If your number exceeds that, it will cause errors. Okay. So, this is important if you are doing C programming, size of a number, especially when you have big data size, then your data index itself will exceed this number. My array is sometimes 2000 cube, okay. Like if I am trying to simulate weather, then my data will be 2 billion, 2000 cube each direction. So, how many point data will be there? 2000 cube will be 8 billion, 8 billion exceeds it. Okay. So, you have to be careful what is your index. I mean, if you have done a bit of programming, you know that array index has to be integer, right. So, I need to say I can't use this integer. This is one common source of error. Okay. So, I have to use long int, this is again part of C, you have to use long int, which allows you to use 8 bytes, and 8 bytes lets you have 2 to the power 63 as your limit for maximum number. This is big number, no data size will be, at least at present, will be this arrays. Boolean in C stores as 0 and 1. In Python, it will, I think it takes 4 bits, but in C it will take 1 byte. It is inefficient, you need only 1 bit, but it will store as 1 byte. So, if you want to use Monte Carlo, Ising spin, so you can pack a lot of spin in a single byte, right. I mean, you can store 60, well, how many, 256 Ising spins. So, we have to, I mean, you have to program wisely, you know, you have to program in a more intelligent way if you want to use that, but C will, this I am basically telling what C. C also has float. Okay, now this is for real numbers. Now, Python real numbers, again it can be of any size. So, these are some differences between C and Python. Okay, you should know this when you are writing in Python, but it will adjust, it will allocate whatever is required. But in C, the real numbers are 4 bytes. Now, I will tell you a little bit later about how it is stored. So, the maximum with a real float, so in C is called float, C float, and you can go only up to 10 power 38, okay, nothing beyond. So, you will be error if your number is beyond 10 to the 38 or below 10 power minus 38. So, Planck constant can be stored, but if you do Planck constant squared, error, right. Planck constant squared will be 10 power minus 68 and error. Okay. So, you have to be careful what operations you are doing. Nowadays is standard to use double. So, double has 8 bytes and 8 bytes can go up to 10. So, E is, you know this notation, E is 10 power. Okay. So, 10 power minus 308 to upper side is 10 power 308. And what is precision? So, with float I can store up to 7 digits. So, precision only is 10 power minus 7. Any number which is lower than, I mean you need precision more than 7 digits, problem with real, with float, but with double you can go up to 15 digits. Okay. So, 15 digit accuracy is allowed in C programming with double. If you want more, sometimes we need more precision, then you need to write program yourself. There are packages which will allow you to use 16 bytes, okay, double of double, but that will be standard. Well, there will be some other function you have to program yourself. Is that clear? I mean this is something which we need to know. I'll let you, I mean I'll tell you a little bit about how Python handles it today only. I mean we will reach there. So, let us do some estimate. So, typical desktop has 4 to 8 gigabytes. Okay. Please look at your info on in your laptop, figure out, I mean you should not be using it as just like a dumb machine, you know, you should know what is there inside. So, how much memory is there, it will come about computer, it will come. To save a matrix, 2D matrix of 1000 cube. So, you are saving a matrix which is not uncommon, 1000 n squared, each n is 10 cube. So, what is the data size required? This will be stored in a RAM, your memory. So, it will be how many data is there, n squared, so 10 power 6, but each of them will require 8 bytes. So, 8 million. Okay. So, 8 million is the size of your array. Okay. So, it will just occupy that much RAM. If you are using float, then it is going to take 4 million. Now, it is not uncommon, we have programmed on this array. So, 4000 cube. Okay. Now, how much is the RAM required? So, how many data points are there? 4. So, 4096 you can approximate to 4000, okay, 496. So, 4 cube is 64. So, 64 billion. So, this is 64 billion, that is your data, this 64 billion. Now, each of them is 8 bytes double. So, it requires 1/4 terabytes, okay, that is impossible in a laptop or a desktop computer. So, you need a supercomputer for this application. Okay. So, immediately you can see that if I want to do realistic simulation, then you need bigger machine. I hope it is clear to everyone. Okay. So, but laptop is also powerful, but you can do your course project with your laptop. But if you want to publish a paper, new result, you need to move on to bigger machine. Okay. So, I will tell a little bit about this. In this course, we will not discuss this. I did offer a course last semester, but if you want, then of course there is a whole new things to learn, how to handle HPC. So, I will just give you a very brief idea about what the computers are, how much power does it have. Okay. The basic idea now, I mean there are different ways to make supercomputers. The one design which is most popular, so there again they are different, some of them are not popular, they are very fast, but they are not popular. Also cost is a big issue. So, the present popular design is connect many machines and make them work together. Okay, it is just I mean more students get more work out, that's about it. It is not that you are making one student very smart or genius or something, you just say, well, every student will work equally and you get work out. So that is the idea of present machine. So you are basically desktop computers connected together. It is not desktop, because if you want to put desktop in a room, how many can you pack in this room? I mean, I could pack maybe 1000, right? I mean, you just fill up everything, maybe few thousand. That is not good enough. Okay, I will show you the numbers. We are able to pack 1 million processors in a machine. Okay, so so the designs basically is you pack more and more CPUs in a clever way. It is a good idea to see our computer center. So there is a room where this big supercomputer is housed. You can't see inside, but you can basically see the racks. So each rack has many processors. Okay, I don't have a picture here, but you can easily see in Google how does it look. Okay, so the IIT Kanpur HPC. HPC means high performance computing. People don't use the word supercomputer anymore. This is more common, HPC, but which is means the same. Okay, so this word called nodes. So each node is like it has more processors. Each node. So each node is like you can think of one motherboard sitting there with some more stuff. So it's like a box this thick. Okay, in fact the size is like this, like a diary. That's called a node. So there are 901 nodes in our machine here. Now if they are working together, you need to make them talk with each other. If they don't talk, work cannot proceed, right? I mean, you may be very smart, but you need to talk with other person if you want to work jointly. So there is a connector, this is called switch, which is InfiniBand switch. Again, is a technical name. There are lots of switches. Most popular is called InfiniBand switch. And so how much is each processor within a node? So within each node there are 2 processors sitting there. Okay. Now I hope you understand, I told you each processor many cores, many heads, okay, but there are 2 processors. So we have 2 Xeon Phi processors, so 2 CPUs and this name called Ivy bridge. So each of them has 10 cores. 10 cores, okay. So 10 heads is really round, the sun, okay. So 10 into 2 is 20. So 20 cores in each node, and it has 128 gigabytes of RAM. Like it's quite huge compared to your laptop. So each node has these specs, and there are 901 of them. Some of them master node has less cores. So overall, if you see the numbers, we got 17,000, okay, or 18,000. That many cores in our HPC, which is a big number. This machine is ranked, was ranked, now it is slipping down, 118 in the world. Okay, so this is called top500.org. So it was 118th in June 2014. Now how many operations can it do? So again the same numbers I told you before. So each core can do 20 gigaflop, okay, 20 giga floating point operations per second. So multiply 20 into 20 cores, right? I said 20 cores in each node, and there are 901 nodes. So it comes out to be 360 teraflop. Okay, so so tera is 10 power 12 or 0.3 peta. 10 power 15 is peta. So 0.3 times 10 power 15 operations per second. And how much power does it take? It takes 370 kilowatt. Okay, it's 0.3 megawatt. So megawatt is the power basically for a village, full village. Or IIT, this will consuming something like 1/4 or 1/5 of the full power. Okay, so it's a big problem how to make it efficient green supercomputers. It's too much of a power. And how much RAM does it have? It has a RAM of 115 terabytes and hard disk 500 TB. Okay, so it's a big machine. Problem is we don't have programmers, so who can use the full machine. So you need to write a program which will use all the machine. Now it's not easy. It should be efficient program. I mean, you can't say, well, I mean, I write something and put it there. So you need to make efficient program, and it's a big task. So let's look at other machines. So top 10 HPC systems. I didn't write the site. You can just look at top 500 top500.org. You'll see more information on these machines. Okay, so I will just show you the top machine. Where is it from, you know, top machine? China. China has the topmost machine. So I hope this is visible, this is like not very clear. So China has the topmost machine, that number 1, and how many cores does it have? So do not worry about inside what is written there, it is a 3 million. Okay. So 3 million is a big number. So 3 million cores sitting there. What is the peak rating of this? Is 33 petaflop. So this is in tera T flops. So it is 100 times faster than our machine. Now how much power does it take? The last column, 17 megawatts. Okay. So that is the power. So it is a huge power. I mean, you need basically a generator, power station, not generator, power station for this machine. So that is where, in fact, that is another saturation. How to make machines which are fast but consume less power. And the candidates are GPUs are one strong candidate, or your mobile chip. So people are building supercomputers using mobile chips. So mobile chip, the limitation is power. So you can, so it is already there. It's a supercomputer using mobile chips. Okay. There are other machines like this is, second is US. So US is the leader in terms of number of machines. So there are 200 from US. China has 100. They are really putting a lot of effort in supercomputing. India is 11th. I marked, just for information, there is another machine sitting in Saudi Arabia. That is where we run. So we have access to this machine, and it is very fast. This machine has 0.2 million cores, and it is 5 petaflop. So number is, in India there is only one machine with petaflop rating, which is in ISC, 1.2 petaflop. Okay, it is the same machine but less cores. So this is about supercomputers. So I need to talk a little bit of software. This again, I will not enforce that you should use Linux, but you should really use Linux as a, this is a what's called cautionary warning. No, you can smoke, but smoke kills. So similarly, you should use Linux. That's good for you. Okay, but if you are like not wanting to change, it's okay. I mean, you can do Python programming in Windows. So I'll tell you which package to install. But the strong, I mean, if you really want to do something good, then you should use Linux. Or Mac. Mac is Linux. Huh? Mac is Unix. So this machine is Unix. Okay, so I should not preach without practicing. So this is Unix. So the thing which you need to know, Unix, you also need to do a bit of tutorial. Not part of the course. I can't do it. But there are nice tutorials to get to know Unix, just for a user. So you need to know what is the directory structure. Shell. Shell is, so there is a operating system sitting at the bottom. Operating system. Okay. So hardware without a program is nothing. Okay, you can't use it. So program which runs, makes this hardware alive, is called operating system. But operating system programming is very difficult. I can't do it. Okay. So the computer science, they are very smart people who program the operating system. So this is called kernel, Linux kernel. Okay, if you use the word kernel. But kernel is, those things are not easy. So there is a layer above the kernel. So there are realities of different levels. So this is called shell. Shell will talk to the user. Is that clear? So there is a person boss sitting inside, who is the kernel, but the secretary is sitting outside, which is a shell. So you talk to the secretary. You really can't talk to the boss. Well, I mean you can, but then you require some special permission. So shell is what we need to talk. And shell has these commands. I mean, if you know a bit of Unix, so, or some of you are probably experts of Unix. Okay, so ls for listing directory structure, a cd change directory. So these are the commands you need to know. Tutorial, you basically you need to spend maybe 3 hours, and you can get to a big reasonable user of Unix. So this one site, I'll post it in a website. Well, I'll probably do something so that you can get access to my PPTs. And you need an editor. Okay, for using the CC machines, you need an editor. It's Linux machine, CC machines. So the editor I recommend is gedit. Okay, so that's part of Linux. There are other editors, VI. VI is not so good. I mean, again, it's like a cryptic VI or Vim. I recommend gedit. Okay. But please get used to it, otherwise you can't do your homework. Okay, you need to use one of the editors. And I think this slide is probably ending. So that is one. So Linux is one. Well, Linux derives itself from Unix. Okay, Unix was a very clever design. It's one of the best thing which happened in last century. Okay, best including science and engineering. Okay, Unix is a very clever fundamental design done in Bell Labs, but it was made for workstations or well, basically workstations, IBM and so on. It was 70s. Okay, so but in 90s there is a Travas, Linus Travas. He could port it to desktops in 90s. So desktop had less RAM. So actually operating system sits in the RAM. So it will take space of the RAM. Okay, if you don't have enough RAM, then hard luck. You can't put in Unix. Unix is it's a good OS. Okay, now I will not tell you why it is a good OS. It doesn't have virus. It is secure. So all that features are there. So he could push the subsection of Unix to desktop, and that is called Linux. Okay, so Linux is Unix for desktops. But it turns out it has evolved. Now supercomputers also have Linux installed there. Okay, and there are probably 500 different variations of Linux, and some are useful for some people like some. So the most popular is Ubuntu, right? So Ubuntu is safe, easy, not probably the best, but for it's like Windows actually. It's easy. So the other OS are Windows, which I don't recommend, and OS X is for Mac, but it is Unix based. Okay, it has a layer above it. So the layer is useful, that it makes my life simple, but it's based on Unix. There's another operating system which is coming up in a big way is mobile OS. So I must say that the iOS is for Mac or for iPhone, and so this is Apple OS for mobile, and this is Android is for by Google. This for other phones. Okay, and the Windows is also has its own OS. The third one I didn't write it here. Okay, so programming languages. So we need to know at least roughly what are available. Well, of course, the languages are probably more than 100. Okay, so you need to know some. At least I don't know the language names of many of them, but they are just huge number, and each of them has their specialty. But as a physicist, we need to know. Well, I don't know Java. I simply don't know Java. Okay, but I should know what Java is for. So these three are quite popular among physicists. The Fortran was traditional. In fact, it is one of the first languages in computers. So you need to know one of the three. Okay, if you want to do computing, you need to know one of the three. We will not do it in this course. The reason is to know this, you need something like 20 lectures. Okay, a Python you will see that is basically 3 lectures. I can communicate. You can become a really good user of Python. It's quick, but C has its own the barrier. So these are called compiler languages. So I didn't mention what is compiler. So it will take this text and it will convert into zeros and ones in one shot. So after you write a program, you need to compile, then you need to execute it. So that's why it is slightly longer process. There will be compiler errors and there will be runtime errors. So error while compiling itself, there will be typos, no? Some typographical error. So it will catch, compiler will catch. Then once you succeed to compile, then you will execute, then you will get some errors. So it's a bit lengthy process. So for first language, I think many of you undergrads know C, right? I mean C was the language. Some people know here C. So in fact, I didn't want to give them advantage. So Python will bring everybody. Well, not that I didn't want to give advantage. Python, people who don't know will be able to, and people who know C Python is useful to know. It's not that is useless. It's in fact is the language which is being used I think I mentioned in the last class that around 20% US universities are using Python as the first language, and I am pressing our CS department to move to Python for the first year. So, other languages which are called interpreted languages. So, Python is one language, MATLAB is another one. So, MATLAB quite a few people know. So, MATLAB, so I will show you, okay, I will just run Python, which very similar to MATLAB. So, like what you did, 2 plus 3 is 5, you can plot, you can do sine of 5 or sine of x. So, all that you can do with MATLAB and Python, but it's a interpreted language, means as soon as you enter it will run. So, we do not need to compile separately. So, as soon as you enter, the computer compiles it without you knowing it. Is that clear? So, you do not have to send a command for compilation. So, it will do compilation line by line. So, that is why it is quick for programmer. Programmer can simply say, well, I am lazy, I just do line by line, I just do not want big program to be written. So, it is quick. So, that is why it is fast to code. So, interpreted languages are slower than compiler languages, because compiler, I told in the last class, is a very intelligent program which will make a efficient object code, efficient zeros and one code, which will give you result which is. So, weather prediction is never written in Python. You can write a prototype, but not in the real with real code, a little too slow. So, typically this language, this program can be 100 times faster than Python codes, 100 times. Okay. People are of course working to make Python fast. I will tell you a bit later, maybe towards the end, how can you make Python fast. But the number of lines we write in Python, the average line is 10 times lower. So, this code could be 1000 lines, this is only 100 lines. Okay. So, that is the plus and minus of these two languages. Okay. So, this is finishes intro to computers, and I think you need to know, it is not that you simply get to programming. So, now let us get to a bit of starting to program. Okay. So, I am starting Python now. Okay. So, we have 7 minutes. So, the first thing is, so Python you can, it has, so Python you can install in different ways. So, one thing is to, there are a lot of, Python is not a single program, okay, single package, it comes with lot of libraries. So, plotting is a different library, linear algebra package is different, there is package for various applications, okay. I will discuss some of it in due time. So, but I recommend that you can install Anaconda, okay. So, this is a package, how many of you succeeded to install this? Great, very good. So, just go to the site anaconda.com, I think, okay, just say Anaconda Python, you will get to the site, and install Python 2, okay, not Python 3. So, I think it is 2.7 is the current one for download. Python 3 is slightly different, but there will be problems. So, the syntax is slightly different, okay. So, it is older, but things will be consistent, lot of. So, the first, well, basically Python 2, okay. So, it is much easier to use rather than installing separate packages. So, SciPy, PyLab, so you do not want to install IPython. So, it will do in one shot.